Okay, this is our 7th lecture in business statistics course, and today we're going to switch gears a little bit. We're going to discuss standard distribution. In fact, this is the most powerful, well, not powerful, but the most popular, probably the most well-known distribution in the entire statistics. That would be normal distribution. Now, before we begin, I want to point out that these PowerPoints are all uploaded in the lecture notes on the Scholar. So it's right here. Continuous random distribution, normal. Okay, so coming back to our lecture. So first of all, let's discuss what are the examples of the continuous random variable. So, as I mentioned to a couple of lectures ago, random variable is something that changes randomly from one observation to another, right? So, can be anything really. Can be the response to the question, how would you rank the experience going to the Chick-fil-A recently? Or it can be person's salary, or the height, or the weight, or the MPG of the car. So something that changes from one observation to another. So when we talk about continuous variables as opposed to discrete, continuous really means that the variable can take any value. Like, let's say, for example, human height. How accurately can we measure human height? Well, usually when somebody asks you how tall you are, you're saying, for example, 5 foot 7 inches, right? That's it. But that doesn't mean that you're exactly 5 foot 7 inches long, right? So you can measure the human height down to the a lot of decimals after the fraction of an inch, right? So therefore, any value for the human height, well, reasonable value, right, is possible. So that is an example of the continuous random variable. So the variable can take any reasonable value, and we cannot list them possibly all the values that the variable can take. There are so many of them. There are infinitely many different possibilities. So since there are infinitely many different possibilities, that means that the probability that that a randomly selected person is, for example, exactly 5 foot 7 inches and not a fraction taller or smaller than 5 foot 7 inches, probability of that is exactly 0, right? That I'm exactly 5 foot 7, for example. Okay, because again, there are infinitely many different numbers. So therefore, it's kind of meaningless to speak about probabilities of, for example, somebody being exactly, well, not 5 but 7 foot long, right? Likelihood of that will be exactly 0. But what makes sense to discuss in relation to the continuous random variables are the ranges. For example, what's the likelihood that somebody is 7 foot 5 inches tall or less? Okay, so here I have different value, but yeah. Or somebody, say, for example, will be between 7 to 8 foot long. Okay, or 7 to 8 foot long. Okay, so therefore, let's briefly talk about probability density function, PDF. Every time when we're dealing with continuously distributed random variable, so the variable that can take infinitely many different possible values, then we're dealing with something that's called PDF, probability density function. What is that? Well, there are two requirements. Okay, requirement number 1. Let's say here I have actually an example, graphical example of just some PDF function. Okay, something that can range from certain value A to a certain other value B. So certain variable X cannot be less than A, but at the same time it cannot be more than B. Anything else in between is possible. Every single value is possible. Number 1, PDF function should always be positive. The reason for that is it's really weird to have negative probabilities, right? So therefore, function is always 0 or above. And number 2, if I take the area under the entire curve, and that applies always for any PDF function, if I take the area under the entire curve, the total area should be exactly equal to 1. In reality, it corresponds to the fact that I may not know exact value of the variable x, but I know for sure that it's somewhere between a and b. Cannot be less than a, cannot be more than b. And 1.0 corresponds to 100% chance or certainty, right? So therefore, what I'm saying really is area under the PDF function represents the probability of a certain value or a certain range of values for the random variable x. Simple as that. Okay. So here is an illustration. Okay. So let's say I have two values, x1 and x2. They're located between a and b, the extreme points. Okay, so if I want to calculate what's the likelihood that let's say temperature, okay, I was kind of trying to think quickly on the feet, what could be a good example? Temperature in the city of Newport News, okay? Temperature in the city of Newport News probably does not go below, let's say, I don't know, minus 20 degrees Fahrenheit and plus 110 degrees Fahrenheit. Any other value is possible. In between, right? So, but it's never below 20, minus 20, and it's never above 110. So therefore, A is going to be minus 20, B is going to be 110, and outside of these two limits, the PDF function is 0. But every temperature in between minus 20 and plus 110 is a possibility. So let's say, for example, I pick certain x1 and x2. Let's say x1 is 50 and x2 is 85. Okay, so what is the likelihood that the temperature in Newport News is going to be between 50 and 85? Well, the probability on any given day, right? Like today, for example, what's the likelihood that temperature today is between 50 to 85? So if I have the PDF function, the probability that I'm looking for is going to be just the area between these two boundaries, so this grayed area. At the same time, I can ask, okay, what's the likelihood that on any randomly selected day, out of the blue, temperature in Newport News is going to be above 85? That is given by the blue area, right? Everything to the right from x2, which is 85. At the same time, what's the likelihood that on any randomly selected day, the temperature is below 50? That's my x1. So my left tail of the PDF area in the left tail will give me that likelihood that the temperature is lower than 50 degrees Fahrenheit. So in other words, probabilities graphically are represented as areas under the curve, under the probability density function PDF. Alright, now let's discuss normal distribution. I'm sure you've seen normal distribution before, so it's going to be relatively quick and painless. Reminder what normal distribution is, and in a couple of lectures down the road, well, probably actually in the next lecture, we're going to discuss why is that that the normal distribution is so popular. I told you that this is probably one of the most powerful and most used distributions in statistics. So in the next class we're going to discuss why exactly that is the case. Okay, but for now, here is the graph, kind of sketch of the normal distribution, and here is the gigantic ugly looking formula that you do not have to memorize. Okay, so from the graph, from this picture, you can see that the normal distribution, first of all, it's symmetric, right? Here is the center, and the right hand side, the left hand side are just mere reflection of each other. Second, it has no boundaries. So in the previous slide I had temperature in Newport News, I assumed never goes below minus 20, never goes above 110. So therefore there are 2 points where the PDF function becomes just plain 0. Well, normal distribution is never 0. So therefore this line can come as close as possible to the horizontal axis, but it never actually touches or crosses the horizontal axis. So therefore it goes to minus infinity on the left side to plus infinity on the right side. Okay. Second is, if you remember our discussion about the shapes of histogram, it's a unimodal distribution, right? And because it's symmetrical, that means that the mean of the distribution, the mu, is the same as the mode. Mode is the tallest point, right, of the distribution, and it is the same as the median. Mean mu is median also is because of the symmetry, right? That means that half of the distribution lies below the mean mu, and another half lies above mean mu, which actually brings up an interesting point I just was thinking about. Since the entire area, we discussed that a couple of slides ago, area under the PDF function is always equal to 1.0 exactly. So area under the normal curve also is equal to 1.0. And because it's symmetrical distribution, that means that if I look at the area to the left from the mean, it's going to be 0.5, and the same exact applies to the area to the right from the mean. Okay, so each one of these halves is 0.5 in the area. So likelihood that some variable x, which is normally distributed, is above the mean is 50%, and the same if it's below the mean, it's also 50% chance. Okay. All right. So in order to fully specify the normal distribution, we need two numbers. One number is the mean itself, and the mean gives you the location of the peak, so where this point is located. The second parameter that we need is sigma, which is standard deviation. We discussed that, I believe, in the previous couple of lectures, right? And standard deviation sigma is the measure of variability. We discussed that. And the variability is the measure of inconsistency. In other words, it's the measure of the spread of the numbers, right? So the higher the sigma, the more spread is the distribution. And this is actually illustrated on the next couple of slides. So right here I have several different normal curves. You can see that all of them have the same width. So sigma, standard deviation for them, is the same. The difference is that the black curve is centered around mean 0, the blue one centered around the mean equals to 1, and the green centered around the mean equal to 2. So you can see that as we increase the mean, the curve, and don't change the sigma, the curve doesn't change its shape, but it starts moving to the right. And the same thing happens if you decrease, right? So if I can go from the mean 0 to -1, -2, the curve will start shifting to the left, and it keeps the same shape. So same variance, different means. That essentially indicates that the shape of the distribution does not change, but the peak, the location of the peak, does move to the right or to the left, depending on in which direction you're changing the mean. Okay, so what happens as we start changing the sigma, standard deviation? Well, sigma is the measure of variability, or in other words, measure of the spread of the numbers, right? So here in this case, I have the opposite example. Mean stays the same, 0, okay? But what I change is standard deviation. So when standard deviation is high, sigma equals to 3, you can see that the distribution is very flat, right? So it goes, and remember we discussed the property of the bell-shaped distributions. Basically, we said that if you go plus or minus 1 standard deviation within these boundaries from the mean, away from the mean, within these boundaries you have about 68% of all numbers in the distribution. If you go plus or minus 2 standard deviations, that gives you 95% of the distribution. If you go plus or minus 3 standard deviations, it gives you 99% of the entire distribution area. So you can informally think of that as plus or minus 3 standard deviations gives you pretty much the majority of the distribution. Okay, so in this picture you can see that if you go well, 3, sigma is 3, plus or minus 3, it will give you plus or minus 9, right? So therefore, well, here we're kind of cutting it off at -8, but -9 supposed to be somewhere over here, right? And that's where the distribution almost meets the horizontal axis. So this one is spread pretty widely when standard deviation is high. The next one, black, when the standard deviation is 1, you can see that the distribution ranges from plus or minus 3 sigma, right? So right here is -3, and that's where distribution gets pretty close to 0. Right here you have +3. Okay, so distribution becomes more, so to speak, concentrated and less variable, less scattered to the right and to the left. And the blue line, 1/2, so 1/2 times 3 gives you 1.5. So here is your 1, and that's roughly 1.5, right? So, and here you have -1.5. So you can see that the majority of the area under the curve is concentrated between -1.5 and +1.5 for the blue distribution, right? So if you keep the mean the same, but start increasing, well, in our case it's decreasing, right? Decreasing the sigma, the distribution becomes less spread and more concentrated, okay? So it becomes more sharp, looks like a single peak, okay, as opposed to kind of smoothed out, fairly spread to the right and to the left shape. Less, it becomes less flat and more sharp, right, as you decrease the sigma. Okay. So big fat question is, okay, so what? How can we use knowledge of the distribution? What's the value of knowing how certain things are distributed? Well, as we go through this lecture, my intention is to show you that in statistics, having a data set is good. Okay, so our analysis so far was centered around, okay, here is the data set, it's saved on your machine as CSV file. Let's find all kinds of numerical measures about this data set, right? Let's find the mean, median, standard deviation, range, interquartile range, first, second, third quartiles, 86th quartile, 35th, not quartile, percentile, 35th percentile. Let's find the value that gives you 0.05 in the right tail distribution. So all kinds of burritos we did, right? Well, if you know how your numbers are distributed, you don't really need to collect any data, because you can find all these characteristics of that you're looking for, numerical characteristics, without collecting single number. So therefore, in statistics, knowing how certain numbers are, certain data sets are distributed is actually even better than having access to the whole bunch of numbers which you collected experimentally, so to speak. Okay, so let's take a look at this problem just to give it, more practical spin. Time required to build a computer is normally distributed with a mean of 50 minutes and standard deviations of 15 minutes. So here we're talking about assembly operations, very much like Dell. Dell, as you know, the company that sells computers, right? It's true that they assemble computers, so they don't manufacture the parts. Dell is just a so to speak a screwdriver operation. Okay, so Dell buys parts and components from multiple suppliers. For example, it buys screens from probably Samsung, LG, Sony, if they're still making monitors. I don't know if they do. They buy CPUs, processors from Intel and AMD. They buy memory chips from, from Kingston, from Micron, from Critical. There's another chip manufacturer. They buy motherboards. They buy computer cases, keyboards, so all components. And all they do is pretty much put them together to create a computer and install software, and that's what they sell to you. Okay. So therefore, for them, it's pretty important that they assemble computer quickly. So in this case, what we're assuming is this: we tracked a number of computers throughout the assembly line, right? So randomly picked a bunch of machines that were ordered by customers, and we tracked from the moment each of these computers, from the moment when the computer just was started on the assembly line up until the moment when it was done, ready to be packaged and put in the box, right? So how much time does it take from the start of the assembly operation until the end, when it's all put together and tested and ready to be shipped? Okay, So different computers obviously require different amounts of time, right? Because first of all, there are different machines, right? One machine requires, for example, 8 gigabytes of memory, another machine requires 4, third machine requires 16. Then one machine can have, for example, 2 hard drives inside, okay, or extra second CPU, for example, dual CPU machine. That basically factors into the very build, right? Different machines require different amount of manual labor, so therefore they take different amount of time to put together. Then there are things like, for example, delays, right? So I couldn't find my screwdriver, so therefore, the assembly time on that computer was a little bit longer, or somebody was out of, motherboards, right? So they had to wait until somebody brings motherboards from the warehouse. So all kinds of things happen in the assembly environment. So now we have tracked and collected a bunch of data on a number of computers, and let's say we plot a histogram, okay? And the histogram looks like this. It looks like a normal distribution. In other words, it's bell-shaped with one single unimodal, with one single peak. Goes down pretty quickly to almost 0 on the right and on the left side. And we calculated the average, turned out to be 50 minutes, and we calculated standard deviation, just like what we did for our data set for, was it phone bills? Can't remember what was that. Not the phone bills. In the previous class, we looked at how do you calculate the averages, or restaurant, right? Time spent in the restaurant. And it turned out to be 10 minutes. Okay, so after that we said, okay, it looks like normal distribution, so let's just assume it's normal. Now, what I wanted to point out in this problem is the following. This is an approximation, okay? Why is that an approximation? Nothing really can be normally distributed. We're kind of assuming that, yeah, approximately, roughly speaking, this is normally distributed. The reason is very simple. Normal distribution, as we discussed, goes to the infinity on the right-hand side and on the left-hand side, right? So that means that if I draw the normal distribution with a mean of 50 minutes and standard deviation of 10 minutes, it will go to minus infinity on the left side, okay? So if I take here the value of 0 minutes, and look at all the values to the left from 0, they are negative, right? So and since there is some area still under the curve, under the normal curve to the left from number 0, that means that I can technically calculate the probability under the curve to the left from 0. And that would be what? Probability that the time that it takes to assemble a computer is negative. How can that be? It's not possible in our physical world, right? You cannot take minus 10 minutes to put together a laptop, right? That's just not reasonable. So therefore, when I say that time to assemble a computer is normally distributed with a mean of 50 and standard deviation of 10, really what I'm doing is I'm kind of saying it's an approximation, okay? This is not exact science anyhow, because nothing is really normally distributed ever, okay? So you will never, strictly speaking, see normal distribution in the real world, but it's a good approximation, okay? So let's use that. Another thing that I wanted to point out is this. This is kind of a shorthand notations that statisticians have adopted for normal distribution. So this line right here that says t tilde n 5010 literally means that variable t, that is time to assemble a computer, is distributed n normally with the mean, the first number of 50, and the standard deviation, sigma, second number of 10. So this is how statisticians avoid writing this long phrase. The time required to build a computer is normally distributed with a mean of 50 minutes and standard deviation of 10 minutes. So this is a shorthand notation for this long sentence, okay? Time is normal with mean of 50 and standard deviation of 10. Okay, so now that we have established this, let's move on and let's take a look at that problem. What is the probability? Somebody, I mean my boss, for example, manager, asks me, Dmitry, can you tell me what proportion of the computers that we put together take anywhere between 45 to 60 minutes to assemble. I want to know, okay? So in other words, that boils down to the question, what is the probability that a randomly selected machine will take anywhere between 45 to 60 minutes to assemble, to put together, okay? And I have to use the normal distribution for that. Alright, so now let's switch our attention to RStudio, because this is where we need to bring up our tool. Remember, about 10-15 minutes ago I told you that knowing distribution is better than having a collected data set. Why? Because if I know a distribution of a certain variable, in this case time to assemble a computer, I can answer all these questions. What is the probability that the computer can take between 45 to 60 minutes to assemble? I can answer that question without collecting single data point from the assembly line. So here is how I can do that. Alright, so and I promised you that everything that I do I'm going to save in the R script, and I'm going to document or comment pretty much every single step, right? So here I'm gonna say time to assemble a computer is normally distributed, and remember I adopted the notation, right? T, normally distributed, is tilde, squiggly line, okay? N, normally, with the mean of 50, and the standard deviation ST equals 10, okay? So first let's answer this question. Okay, so what I'm looking for is what is the probability that it takes between 45 to 50 minutes. Okay, so let me kind of approach that in baby steps. Okay, so first let's find probability that time to assemble a computer is under 60 minutes. Okay, what's the likelihood that I pick a randomly selected computer and time to put it together is 60 minutes or less. Okay, so for that I'm going to use function which is called p norm. P stands for probability, norm stands for normal. Simple as that. Okay, and p norm function, for that function I have to provide several parameters. Okay, and you can see them right here. Okay, so as I type the name of the function p norm, I can see that it gives me, hold on, disappeared somewhere, right? P norm. Okay, so this is called tooltip. I don't remember if I mentioned that before or not. Kind of help that shows up and it tells me what the function is expecting. That's a tooltip. So tooltip is telling me, first you have to provide q, the value for which you're looking to find probability. Next you have to provide what's your mean, then after that standard deviation, and here is another one, lower tail true or lower tail false. Okay, so let's do that. First of all, the value that I'm looking for to find the probability is 60, right? 60. Alright, then next is mean, normal distribution. Again, normal distribution takes two parameters. After that you fully know its shape. One parameter is the mean, another parameter is the standard deviation. Both of them have to be specified for the function p norm. So mean is 50 and standard deviation SD, incidentally it's the same name as the function that calculates standard deviation, SD, right? It's 10. And the last one, since I'm looking for times less than 60, if you can kind of graphically imagine, less than 60 means that I'm looking in the left tail of the distribution. So therefore I'm going to say lower tail equals, and this is logical value, true. Left tail true tells the function look in the left tail of the distribution. Okay, and that's all I need really. So now I'm running this function, and here at the bottom I'm going to give it a couple of entries. It tells me that the likelihood that you select a machine and it will be assembled in under 60 minutes is 84.13%. Okay. Alright, so what if I was looking to find proportion of all computers that take over 60 minutes to assemble? So another way to interpret that number, by the way, is 84.13% of all of our machines are put together in under 60 minutes, right? So obviously you can find it in two different ways. The other question, right? So what is the probability? I'm going to put the comment here, right? What's the probability that time to assemble a machine takes more than 60 minutes, right? So one way how I can do that is obviously copy paste, right? So I'm going to another thing that I have an advice for you is programmers should be lazy. If you can avoid typing something, avoid typing something. You can just copy paste. All right. So since p probability of time greater than 60 represented by the area in the right tail of the distribution, then everything else remains the same. The value is 60, mean 15, SD is 10, but lower tail is false now, right? Lower tail false means it's upper tail. That's right tail. Okay, and the probability is 0.1586. Okay, so this is one way to do it. Alternatively, here's what I can do. Remember the property of the PDF function? The area under the entire curve is 1.0. The area in my left tail, this one right here, one that I calculated first, was 84.13. So what's the area in the right tail? To the right from number 60. It's 1 minus the area in the left tail, right? So I can just simply copy paste the area in the left tail, run this line, and it'll give me exactly the same answer, right? So I can either say literally what this says is do not look in the left tail, right? In the lower tail. Look in the right tail. Or this one says, okay, you can actually look in the left tail, but then after that you have to subtract that from 1. And the answer is the same, okay? Alright, but my question is, of course, originally, let me bring up my PowerPoint back, right? My question was, what is the probability that the time that it takes to assemble the machine is between 45 to 60 minutes. So I found probability that the time is under the 60 minutes. How about 45? What do I do for that? Well, let me show you. I actually drew the picture right here, okay? So graphically, the probability that I'm looking for is this shaded area, blue, right? This is my normal distribution. The peak is 50 right here, and the standard deviation is 10. Well, you can see standard deviation on the picture, right? It's just basically how wide is the distribution. So graphically speaking, I'm looking for the area between 45, which is right here, and 60, which is right here. So one way how I can find it is this. I know the area to the left from 60. What I can do is I can take the area to the left from 45 and subtract from the area to the left from 60, right? So this big area, 60 and less, minus this smaller area, 45 or less, that will give me the area between 45 and 60. So in other words, going back to RStudio, if I want to calculate the probability that time to assemble a computer, so I'm going to put it right here, time to assemble a computer is going to be between 45 to 60 minutes. Here's what I can do. I can take the big area to the left from 60. It's the first one which I created, right? Subtract from that a smaller area to the left from let's see, 45, and that will give me the area between 45 and 60, right? Okay, so and when I run this line, that gives me 53.28, so almost 53.3. So about 53.3% of all of our machines manufactured by Dell or whatever that company might be, right? It takes between 45 to 60 minutes to assemble. Okay. So it should be fairly straightforward. So here we were calculating probabilities by not knowing the value, such as 45 or 60 minutes, right? We could calculate the probabilities. All right. So now, and all of that is in your slides, basically. Okay. Now let's talk about the reverse problem. How about if I know the area under the line? So essentially, in this part, what I was doing really is I knew the value, 45 minutes, or 60 minutes, or whatever it might be, and I could calculate the probability or the area under the curve, to the right from this value, to the left from this value, etc., etc. How about the reverse problem? I know the area under the curve. Can I calculate the value of the variable that gives me this area? And again, the area can be either in the right tail of the distribution or the left tail of the distribution. So here in this picture, on this slide, what we new notations, I guess, right? So if my area in the right tail of the distribution is equal to some number a, and the value x, random variable value, that gives me this area, I'm going to abbreviate as x with a subscript a. Okay, so if a, for example, is 0.25, right? X is 0.25, then this abbreviation would be x with a subscript 0.25. That means that to the right from that x sub 0.25, I have the area under the normal curve, in this case normal curve, 0.25. Okay. Alright, so in order to find the values, so let me go back to the RStudio, right? We were looking for probabilities by using the function p-norm. P here stands for probability. Norm stands for normal distribution, right? Probability p for the normal distribution. In this case, when we know the area and we need to find the value, we're going to be using function q-norm. Okay, so it's still for the normal distribution, but we're looking for the q. I guess it stands for quantity or quantile. Okay, and it works in exactly the same way in terms of what it takes, just like the function p-norm. So, for example, here, okay, computers that take that have extra features. So they have extra details that require extra testing or extra software installation or whatever that is, right? Take longest time to build. How much time does it take to build 5% of the computers that have the most extra features and therefore take the longest time to build? So, in other words, we need to find such value t sub a that only 5% of the values of the distribution is above that t sub a, right? So in other words, since we agreed just 2 slides ago, right? The area to the right from the variable becomes the subscript, right? So since the area to the right from this value ta is 0.05, that would be 5%. 100% is 1. 10% is 0.1, 5% is 0.05, right? So the area to the right from t sub a is 0.05, so we're looking to find actually such time that only 5%, 0.05, is of the entire distribution is to the right, in the right tail from that value. And why is that in the right tail? Because I'm talking about computers that take the longest time to build, right? If you kind of imagine where on the horizontal line the longest time, it's on the right, in the right direction, right, in the right tail of the distribution. Okay, so let me switch back to RStudio. So here I'm looking for, and essentially I'm looking for quartile, right? How so? Well, I'm looking for the value such that only 5% of the data is above that value, and 95% of the data of all these computer assembly times are below this data. So essentially in this problem, this question, I'm looking for the 95th percentile. Okay, so I'm gonna type here that 95th percentile or t with a subscript 0.05. Can't really do subscript in the RStudio, so I'm going to just say t is 0.05, right? Okay. And I'm going to use q norm function. So p is for probabilities, q for quantiles, right? Q norm. And as I mentioned just a minute ago, it works in exactly the same way as the p norm function. So I have to specify, but now instead of value, right, q norm should give me the value. So what it takes is the probability, right, or the area under the curve. So my probability, the area is 0.05, okay, and I have to remember that's in the right tail. Then I have to say what's the mean. Mean is 50, and standard deviation SD is 10. And how do I say I'm looking in the right tail of the distribution? Well, I have to say that the lower tail is, if I say true, that means the left tail, but it's not, right? I'm looking in the right tail, so therefore lower tail is false. Look in the upper tail, the right tail. And when I run this line, it's right here, okay? So the answer for me is the 95th percentile of my normal distribution is 66.44. That's the statistical language, right? That's in terms of statistical lingo. So if you want to translate it into the human language, the way how it sounds is 5% of the computers that have most extra features take us 66.45 minutes or higher to assemble. And therefore, the majority of the computers, 95%, take 66.45 minutes or less. Okay? So that answers the question, basically, that we saw in the slide, right? So that's how you use the function p-norm to find probabilities given value, and q-norm to find the value given the probability. So these two are reverse problems, essentially. So graphically speaking, here's what we just did, okay? This is normal distribution with a peak at 50 and standard deviation of 10. 5% of the most complicated computers take longest time, so therefore they're in the right tail of the distribution. So this blue area is 0.05, and the value that cuts 0.05 in the right tail is what we just found, 66.45. Okay, so let's see. Do we have time for this financial example? Well, let's try at least. Okay, so as I told you before, we're going to try and keep the problems in this class as relevant to 4 different functional areas of the business, accounting, finance, management, marketing, as possible, right? So here you go, financial example. A return on investment. Every time when you invest money in anything, in stocks, bonds, right, there is always a risk that you will not get your money back, right? There is a chance that you will earn something, and there is a chance that you will lose some of your investment, if not all of it, okay? So, certain financial vehicle, instrument, okay, is the return is normally distributed. If you ever bought any stocks, there is always it's like a sales speech, right? So our past performance, last year our return on investment was 15%, 2 years ago it was 10%, and there is always like asterisk, legal disclaimer. Past performance is not indication of the future performance, right? So you cannot basically tell them, how come I lost money if you promised guys that you're going to make me 15%? No, we didn't promise that. We said last year it was 15%. We have no idea what is going to be next year, right? So therefore, every time when you buy stocks, it's a gamble, right? So you can lose money, you can make money, you can lose big, you can win big. Nobody really knows what's going to happen. Okay, so you decided to invest something. So historically, people who invested, here's what happened. The returns, in terms of the percentage, right? Percent return, were normally distributed with a mean of 10 and a standard deviation of 5%. Okay, so in other words, I'm going to switch over. So this is my time to assemble computer. Now I'm going to take a look at a different problem, right? So I'm going to financial investment. Financial investment. Okay, example. Okay, so what my problem is telling me that return, let me call it R, right? R for return, that's my random variable, is normally distributed, right? We're using the notations that we discussed. R is normally distributed with the mean of, what was the mean? Was it 10%? So 10, okay, and the standard deviation SD of 5%. Okay, beautiful. So what happens if mean returns remain the same? Oh, first of all, here, right? This is the first question. What is the probability of losing money? What does that mean, lose money? If your return is 0, that means that you didn't gain anything and you didn't lose anything, right? But if your return gets negative, that means that you're losing money, okay? So therefore, what I'm looking for really is, if you can imagine the normal distribution with the peak at 10, standard deviation of 5, and everything below 0, that's loss, right? So if my return on investment is 0 or less, that means that I'm losing money. So really, what I'm looking for to find, right, for this first question is probability that the return is going to be negative. Negative return is the money loss, okay? So which function do I use? P norm or Q norm? Well, because it's talking about probability, this should be P norm, right? Probability for the normal distribution, okay? And the value that I'm looking for is 0, okay? The mean is 10. Standard deviation SD is 5, okay? And is that the right tail or the left tail? Well, the peak is at 10. I'm looking at 0 or below, so that means it's a left tail. So therefore, you have to say lower tail is true. Whoops. See what I did here? I actually typed them lowercase. Do not do that. This is a mistake. It should be all uppercase. We discussed that in the first couple of lectures. R is case sensitive. So capital true is not the same as lowercase true. In fact, lowercase true is nothing for R. It doesn't understand what it means. Okay, so I'm going to run this, and bam, there is only 2%, 2.2, well, 2.3 roughly speaking percent chance that if you invest into this, whatever it is, stocks, municipal bonds, or whatever that might be, there is a 2.3% chance that your investment is going to start losing money instead of earning money for you, right? Okay, so I hope that was fairly clear. What happens if the mean returns remain the same? And that should be 10%. So I made a boo-boo, that's a typo here. Mean returns remain the same, but the standard deviation increases from 5% to 10%. Okay, well, let's see. So graphically, fortunately, I cannot kind of draw the picture right on the screen of the machine. So we discussed that standard deviation, the mean remains the same. That means the peak stays in, wherever it is. But as I increase the standard deviation, the distribution becomes more flat and wider, right? And that results in a bigger tail. So I'm looking again for probability that the investment will lose money. So it's going to be still to the left from 0, right? Negative return, less than 0. But since the distribution became more flat and more spread to the left and to the right, that means that my tail below 0 is actually bigger for the standard deviation of 5 than it was for the standard deviation of 10. So therefore, the likelihood to lose money should go up, right? Well, let's calculate that, okay? So now I'm looking that the this investment that I'm about to make, R, now is normally distributed like this, okay, with the mean of 10, so mean didn't change, but standard deviation did, right? So standard deviation is also 10. Okay, so I'm looking for the probability again that my return is negative, less than 0. There you go. So once again, it's P norm. below 0, so 0 is my value. Mean is 10%, the average return, but the standard deviation is also 10. And where do I look? Lower tail. Yes, sir. Sure. Lower tail. Bam. And you can see that my risk increased, right? So once you increase the standard deviation of the distribution, your risk, which for 5% standard deviation, the risk was 2.3%. When the standard deviation doubled from 5 to 10%, now my risk is close to 16%, right? So therefore, the point of the story here is, in the world of finance, standard deviation is viewed as the measure of risk of losing money, okay? So standard deviation, for those of you who are going to become, I believe at least one person is going to become a finance major, standard deviation is the measure of the risk. The higher the standard deviation, the higher the risk, financial risk, okay? All right, so, okay, let's see, we have time to go over these problems, probably not. Okay, well, let's go actually through a couple of them, okay, quickly. So these two. Find such value of the return, X%, whatever it is, that the probability to get even higher return is only 10%. Okay, so now what I have actually is the reverse problem, right? So I'm going to go back, right, from 10% for the mean and 10% for the standard deviation to 10% and 5%. So what was that originally, okay? So find such value of return that the likelihood to get even higher return than that, more than X, okay, is only 10%. Well, that means that I'm looking to find the value of the return, Q, right, such that in the right tail of my normal distribution, I have the area of 0.1, 10%, okay? So this is a reverse problem, okay? I know the area in the right tail in this case, and I'm looking for the value, the amount of return that gives me that area, right? So I'm gonna make a comment here. Okay. So find, and really what I'm looking for is 90th percentile, right? Because only 10% are above that number, and 90% is below that number. So I'm looking to find return with a subscript point 0.1. Okay, it gives me 10% in the right tail of the distribution. So in other words, probability that the return, so I'm gonna say IE, probability that the return, actual return, is going to be higher than this R with a subscript 0.1 is only 1% chance, 10% chance, right? So here I have to look for the value Q, right? So therefore I'm going to use the function Q norm, the reverse function, right? So the probability is 0.1, okay? Mean is what, 10. Standard deviation of this instrument is 5. And where am I looking? In the lower tail or in the upper tail? Well, since the likelihood that the return will be higher than that is 1%, and I'm looking in the right tail of the distribution. So therefore, lower tail should be false. And 16.4%. Okay, there is only a 10% chance. So variable interpretation now, okay? The answer that we received is in statistical terms, right? What I found is 90th percentile, really, okay? So 90th percentile of my normal distribution is 16.4%. Okay, now human interpretation. There is only 10% chance that the return on my investment is going to be 16.4% or above. 90% chance that it's going to be 16.4 or below. Okay, that's my human or business rather interpretation of this result. Okay, and let's do this one, and that would be the end of this lecture. Okay, find such value of the return that the probability to get even lower than that is only 21%. So now I'm looking in the left tail of the distribution, right? Here I was looking for the likelihood to have a high return. That's why I was looking in the right tail. In this question, probability less than y. So I'm looking in the left tail, and that's the only difference, right? So let's go ahead and do that. So here I'm looking for 21st percentile, right? Likelihood that the return is going to be less than that. That's what I'm looking for is 21%. That means 21st percentile. So I'm looking for R. Oh, and by the way, what R should I use? Remember, R subscript is always the area to the right from that value. So below R should be 21%, and that is in the left tail. So what's in the right tail? It's 1 minus 0.21, right? So therefore R should have subscript 0.79. Or in other words, here I'm going to say i.e. probability that the return is going to be even lower than that value, R 0.79 is 21%, 0.21, right? 79%, 0.79 is the area to the right, 21%, 0.21 is the area to the left from that value that I'm looking for. And again, using Q norm, right? Q to find the values, P to find probabilities if you know the values. So I'm looking for 21%. Okay. Mean is the same. It's 10. Standard deviation SD is 5. And since I'm looking for the area for the values of the return are less than that, right? Less than R subscript 0.79, then the lower tail this time around I'm gonna say true, right? Only 21% chance that the return is going to be less than that value that I'm looking for. Bam. Okay, so 5.96. Okay, there is a 21% chance that my return on investment is going to be less than 5.96, and there is 79% chance that it's going to be above 5.96. Very decent return, if you ask me, under the current circumstances. Okay, so that concludes our brief lecture. Well, not so brief, actually, it's close to 1 hour, about the normal distribution. And in the next part, we're going to discuss a special normal distribution, which is called standard normal.